All right, if I have you looking at the sun is mostly hydrogen. Hydrogens are lighter elements. They're going to fuse together. They're going to come together and make a heavier element. All right, two hydrogens are going to fuse together and make helium. Our sun is a medium star. It's not that large, it's not that bright, it's just a medium thing. There's nothing major about it. If I'm looking at a star is just a body of gas that emits a lot of energy as either heat or light. If I have you use your reference table, page 15, now I'm at the top, characteristics of stars. These are all stars on here. All those dots represent stars. If you're looking, the colors of the stars vary. That's because the temperatures vary, and how bright they are also vary. Those stars that have a higher luminosity or are towards the top of the graph, they're burning a lot of energy at once. So with that one, they're actually going to die quicker because all that energy is going into burning or producing lights. If I have you look at your reference table, at the very bottom, it's a different graph than what you're used to seeing. You're used to seeing lower values on the left, higher values on the right. You're looking, your higher temperatures are on the left and your lower temperatures on the right. Color-wise, blue is your hottest stars. Red are your coolest stars. If you look at the sun and read straight down, we're a yellow. All right, so we're kind of in the middle. But we also, if I look vertically up, my luminosity, we're kind of a medium. We're not really bright and we're not really dim. Everything actually here is based on Earth. So the further I go to the left, the hotter my stars. The further I go to the right, the cooler my stars. Higher I go up, the brighter they shine. The lower I go down, the dimmer they are. Now, in a minute, we're going to talk the life cycle of a star. Some of those are actually on this reference table. You'll see dwarfs, main sequence, giant, and supergiants. So how does a star begin? Star begins as a cloud of dust and gas. All right, mostly hydrogen. You're looking about 70% hydrogen, 28% helium, and 2% heavier elements. Well, it has a weak gravitational attraction between each other. If you have a neighboring star that explodes and gives off energy, that would cause that nebula to actually force material closer together. When you force the material closer together, you increase the gravitational attraction. With that one, as they get closer together, you also start producing friction. Friction gives you heat. All right? As it's getting closer together and producing more and more heat, it's going to start spinning. So my nebula eventually is going to go into my protostar. My protostar is when my star is actually born. It's when I first get nuclear fusion. Remember, fusion, I'm putting less or lighter elements together and making them more dense. So main sequence star. Main sequence star is what our sun currently is in. It will stay a main sequence star as long as it has enough hydrogen to fuse to make helium. So if you listen to astronomers, they say that our sun is about halfway through its life as a main sequence star. So in about another 4.5 billion years, it's going to run out of fuel. So it's going to run out of hydrogen to fuse to make helium. That's going to cause it to contract down to the core. All right, that's going to get re-energized, and then it's going to expand. With its expansion, my helium is going to fuse with my carbon that's in the core. With that one, my star expands. Now, there's some debate with scientists. Will our sun, when it becomes a giant, and it's not going to become a supergiant because it's too small of a star, will it incorporate and incinerate the first 3 planets or the first 2 planets? Doesn't really matter because in 4.5 billion years, I don't plan to be here. So if I'm looking at that one, a giant is approximately 10 times larger than our sun currently is, whereas a supergiant is 100 times or greater than what our sun currently is. Remember, our sun will never be a supergiant. The next stage is going to be my dwarf. Once my star runs out of helium, it's going to lose the outer gases. It just leaves the core. Now, it can stay illuminated for millions of years before it fizzles out to nothing. With that one, we also have to remember that the light that's shining from those distant stars, some of the light left those stars hundreds of years ago. So with that one, we don't know if they're actually still shining. The next option, nova or supernova. My dwarf my dwarf star gathers neighboring star energy, and that's going to cause it to explode. Now, if I follow the life and death of a star on your diagram, a couple options. Ours, main sequence star, we're going to do the bottom one. Average star, it's going to be a red giant, planetary nebula, white dwarf, black dwarf. If our star was a lot larger, supergiant, supernova, either a black hole or a neutron star. All right, you need to talk Big Bang Theory. Big Bang Theory, not only is it a TV show, but it's a theory of how the universe was created. All right, scientists used to think it was like their universe was 17 billion years old. With technology, they have it down to around 13.7 billion years, but anything between 13 and 15 billion years is accepted. Now, they're looking for using spectrum. So they're looking at, when you look at a spectrometer, you actually get different wavelengths that spread out depending on the composition of the star. All right, with that one, you can find the composition, but they're also trying to figure out, are the stars coming closer to the Earth or are they getting further away from the Earth? If I have you look at your reference table, page 14 at the bottom, electromagnetic spectrum, you'll see the left side, the wavelengths are decreasing, whereas the right side, they're increasing. I need you looking at visible light. So if I look at visible light, violet, blue, green, yellow, orange, and red, notice the violet blue side is in the decreasing wavelength side. So that would mean the stars are getting closer to the Earth because the wavelength is getting smaller. If you look at the red end of the spectrum, it's on the increasing wavelength side. So that means the star is getting further away from the Earth. What scientists have found is we have a red shift. That they're actually, the universe is expanding, things are moving further away from each other. Constellations. You already had that as a vocab word, constellation, group of stars that form an image. You're looking at alpha star is your brightest star within the constellation, beta star is your second brightest. If I look at my Ursa Minor, Little Bear, Polaris, remember it's part of the Little Dipper, which is part of the Ursa Minor. Polaris is your alpha star, or your bright star. So we start with Earth, our sun as our star, part of the solar system. Our solar system is a part of a galaxy. So there's billions of solar systems within a galaxy. So this one, we're part of the Milky Way galaxy. All right, the Milky Way galaxy is a spiral. Galaxies are classified by their shape. I look for our solar system is located on one of the arms of the spiral, about 2/3 of the way from the center. All right, I hope you enjoyed your astronomy.